This video will show the difference between a linear and an exponential model. The difference between the two can be made clear by the following example. Suppose after graduating from college, Tristan receives two different job offers. They both pay a starting salary of $50,000 per year. But one of the job promises a $2,500 raise each year, while the other job guarantees a 5% raise each year. So to be clear, the first job is going to simply add $2,500 to Tristan's salary each year, regardless what his previous salary was. Anytime something goes up or down the same amount each year, that would be the definition of linear. The second job will not raise Tristan's salary the same amount each year because it's based on the salary the previous year. It says they're going to raise his salary 5% each year, implying 5% of whatever he made last year. Anytime something changes the same percentage each year, that is the definition of exponential. Let's make out a couple of table values to make this even clearer. Let's fill out this table that represents Tristan's salary over the first 20 years if he chooses the first job offer that raises his salary $2,500 each year. So if t is equal to 1, what would this sentence say if I replace the letter t with the number 1? It says that my output will be whatever Tristan's salary will be after 1 year. So what will his salary be after 1 year? The problem stated that he started at a salary of $50,000, but after 1 year, he should get his first raise. So to calculate his raise, we will take $50,000 and we will add $2,500 one time. That would be $52,500. Now it turns out that the actual answer here isn't what's most important. To find an easy way to find out the cells below, I want to identify a pattern in the numbers. So for example, rather than just calculating his salary for the second year by taking the first year's salary and adding $2,500, that would be the easiest way to fill out this cell. That would be more difficult down here when there's a 10-year jump, because you have to repeatedly add $2,500 many times. So if you let me illustrate this a different way, his salary after the second year can be thought of as he started with a salary of $50,000, we added $2,500 to represent his salary after 1 year, but now that since we're looking at his salary 2 years after he started, they will give him another raise of $2,500. So this looks actually like I'm doing more work than needed, but here's the power. Notice that this statement can be written as 50,000 plus, and then repeated addition can be represented by multiplication. We added the same number twice, and in math, we can use multiplication to represent that. We added the number 2,500 2 times, so we will times this number by 2. Multiplying 2,500 by 2 is the same as adding 2,500 2 times. So if you want to do this on a calculator, type in 50,000 plus his raise is $2,500, then we need to multiply by how many raises he got. Since this is year 2, he got 2 raises, so that would be $55,000. Again, you could get the next cell by simply adding 2,500 again, but since the point of this video is to recognize a pattern and help us fill out the later cells in an efficient manner, I'm going to think of year 3 as that he started with 50,000 and we gave him 3 raises. You add the number 2,500 3 times. Once to get from his starting salary to what it was after 1 year, a second time after year 2, and now a third raise after year 3. This would be easier if you thought of it as his starting salary is 50,000. We are repeatedly adding the same number each time. It's just a matter now of writing in parentheses how many times we need to add the raise. This is after 3 years, so Tristan should have 3 raises, so we'll put a 3 here. So in my last example, I literally can go up a couple times, press enter to copy that, Or if you're on an older calculator, you can press the second key and then enter to copy the previous command line. I'm going to left arrow change this to a 3 and find that after 3 raises of $2,500, Tristan's salary would be $57,500. It's interesting to note that after his first raise, that we could put a 1 here to represent that we added a $2,500 raise one time to his starting salary of $50,000. So if you looked at all of these statements in the right way, they lead to an equation. They all start with the number 50,000. That does not vary, so we don't need a variable at this point. They all have a plus 2,500 in them. The only thing that varies from one of these answers to the next is the number in the parentheses, the number of raises Tristan receives. The number in the parentheses changes from 1 to 2 to 3. Since that number varies, we need a variable. We've been defining that variable as t. So t would be the number of raises after 2 years. So now when we get to filling out the rest of the chart, we don't need to add $2,500 over and over again. We simply need to identify that after 5 years of working, he will have had 5 raises. So his salary would be starting at $50,000. We would add the same raise each year for 5 years. This cell would be, he started with $50,000, got many $2,500 raises. In fact, he got 10 raises. So we put a 10 in the parentheses. And then finally, after 20 years, he should get his 20th raise. His starting salary was always the same, $50,000. His raise is always the same, $2,500. And he's getting 20 raises. So I can either press the up arrow a couple times, or I can press second enter, and I can change these numbers. I'll change the 3 to a 5. Press second enter, change the 5 to a 10. I typed over one of the parentheses, so I need to put it back. And then finally, I'll press second enter and change the 10 to a 20, and simply copy these last 3 numbers into the chart. Boy, I want Tristan's job because he's going to make $100,000 after 20 years. So in a moment, we'll compare these values with the chart that will represent his salary if he was to choose the second job offer. He starts with a salary of $50,000, but instead of adding a $2,500 raise, they are going to increase his salary by 5% each year. Remember that the salary is defined to be his salary after 2 years. So after 1 year, he should get 1 raise. So we need to raise his salary one time by 5%. So one way to find his salary after 1 year is to take his starting salary, and we need to add the 5% raise. So we need to figure out what 5% of his starting salary would be. So we would add 0.05, that's 5% as a decimal, multiplied by his starting salary of $50,000. As usual, I'm going to try to show you a shortcut to this. Notice that I have 2 terms here, and both terms have the number 50,000. When that happens, you can factor that out. If I take 50,000 and I factor that out, I would get the number 1. 50,000 times 1 gives me 50,000, his starting salary. But then we added the raise, and if I factor out this 50,000 here, I would be left with 0.05. So factoring out the 50,000 in the second term, I get 0.05. And if you see by the distributive law, distributing the 50,000 to the 1 gives me his starting salary, and then distributing the 50,000 to the 0.05 adds on 5% of 50,000. The reason I show this is that the number in the parentheses can be simplified. 1 plus 0.05 is simply 1.05. So rather than doing this 2-step process, I can simply take his starting salary of $50,000 and multiply by 1.05. Let's do that on the calculator. So let me clear my calculator. So he started with $50,000, and I'm going to increase his salary by simply multiplying by 1.05. I would just put that in parentheses. knowing that there's implied multiplication here. Pressing enter, I find that Tristan's salary is $52,500, which turns out to be exactly what Tristan's salary was after 1 year in the previous job offer. So this was his salary after one raise of 5%, and we got that number by taking 50,000 and multiplying by 1.05. So to find his salary after the second year, one way you could do that is to simply multiply by 1.05 again to get that 5% increase. It's important to note that the operator here is multiplication now rather than addition. When he was getting the same raise each year, in the linear example, the pattern was to repeatedly add. But now that we're on the exponential example, where his salary is going up the same percentage each year, the pattern will be to multiply. So I can think of his salary after the second year as being whatever it came out to be the first year. I'm copying that down. So in your mind, think of this number is what we put on the calculator to get his salary after 1 year, the $52,500. So this is his previous salary, and now we need to give him one more raise since 1 year went by. So we would do that by taking his previous salary and multiplying by 1.05. Well, as usual, I'm trying to see a pattern. This statement can be simplified as he had a starting salary of $50,000. We're multiplying by 1.05, but we did that 2 times. In math, 1.05 times 1.05 can be thought of as 1.05 squared. So to show you this is the same, on my calculator, I could just press the multiplication key, and my calculator assumes I'm talking about taking the previous answer of $52,500, which was his salary after 1 year, and multiplying by 1.05. That method gives me $55,125. I took his salary after 1 year and multiplied by 1.05. My other method, which will work well when we get to the bottom of the chart, says we could have just started with $50,000, and then we just tell the calculator how many times to give Tristan a raise by using an exponent. So we raise to the second power, or square it. It's important to realize that in mathematics, exponents represent repeated multiplication. We multiplied the same number twice, so we use an exponent of 2 to denote that. Pressing enter, notice in one line I get his salary after the second year, $55,125. Since I'm now an old man, I better write that down before I forget it. So I'm just going to use the same technique I did before. To find his salary after 3 years, I will argue that he started with $50,000. We give him a 5% raise for 1 year. We give him a 5% raise to get to the second year. But now that he's been working there for 3 years, they would raise his salary one more time. But in mathematics, again, we can represent that repeated multiplication of 1.05 by just raising to an exponent. There are 3 factors of 1.05. So we will put a 3 here. So you can see the advantage now that you can see a pattern. In fact, to see the pattern, you could think of this first raise as being they raised his salary by 5% one time. And just like I did in the previous example, I'm going to use the pattern to help me fill out the rest of the chart. And what I've done in a very sneaky way is showing you how to find a formula for an exponential function and also make sense of why the formula is the way it is. So notice in each of these iterations, 50,000 never changes. And in each of these boxes, the number in the parenthesis never changes. It's always 1.05, and that makes sense because his raise is always 5%. The only thing that changes or varies, which indicates a need of variable, is the exponent changes from a 1 to a 2 to a 3. But those exponents match the numbers in the chart here, 1, 2, and 3, which is what we're calling the input variable t. So all I need to do is put a t here as a variable to represent that time varies in this problem. So to fill out the rest of the chart, especially since it starts skipping several years, I'm going to use this shortcut where I start with 50,000 and I'm going to give Tristan a 5% raise, and the exponent would just tell me how many raises I need to give. For this cell, that would be 5 raises. In this cell here, after 10 years, Tristan will have had 10 raises. So I'll take his starting salary of $50,000, give him a 5% raise 10 times. The number 10 tells me how many times to multiply by 1.05, which is the number of raises he gets. So finally, this will be 50,000, a raise of 5%, and this last cell represents his salary after 20 years. Now I need only type all these values in the calculator and fill out the chart. So in my calculator, I have his raise after 2 years. I'll press second enter. I'll left arrow and just change the 2 to a 3. That didn't work. This was supposed to be an exponent of 3, not multiplication by 3. Not sure why that happened. Let me go up and grab that one again. Or if you're on an older calculator, press second enter a couple times to get that. The reason what I did here didn't work is because the 2 was obtained by using the squared key, not the caret key. So let me delete the 2, press caret, and press 3. Because my calculator is in classic mode, it's not putting the 3 up in the exponent position. Now either go up a couple times and press enter to copy that, left arrow, change the 3 to a 5. Keep repeating this process. This time I'll press second enter, left arrow, type over the 5 with a 10, press enter. Finally, I'll press second enter, left arrow, and change that 1 to a 2. Now that I have a 20 in the exponent, I press enter. Now I need only copy these 4 values in the chart, and since this represents money, I will round to the nearest cent. On the calculator, this came out exactly 0.25, so there's no rounding here. On the calculator, this came out to be 0.078. Since this number is 5 or higher, I will raise the 7 to an 8. On the calculator, this came out to be 0.731. Since this number is smaller than 5, I will not round the 3. And finally, on the calculator, this came out to be 0.885. And since this number is 5 or higher, I will round this digit to a 9. So now the question everyone's wondering is, which salary method is better? Well, I made the comment that I'm an old man and I forget things, but I do remember that in the first job offer, after 20 years, he was making $100,000, and clearly he's making more here. So let's discuss why that is. So here are the 2 salary methods set side by side. Notice after year 1, Tristan would be making the same amount of money. That's because a 5% raise based on a $50,000 salary is a $2,500 raise, which is what he was getting with this company. The difference is, though, since this was linear growth, the method of raising his salary did not depend on the previous salary. They always added $2,500 regardless of what his previous salary was. So the amount of increase is constant. That's the definition of linear, is that the rate of change is constant. It goes up the same amount each year. With exponential, however, the change is not the same amount each year. From his starting salary of $50,000, his salary did go up $2,500, but now that he had a larger salary, the amount of increase is going to be more, because this method always bases the raise on what his salary was the previous year. His salary is no longer $50,000, so the raise is not 5% of $50,000. His raise for the second year would be 5% of a bigger number, $52,500. This is easy to illustrate on the calculator. If you took $50,000 and multiplied by 0.05, this would be the amount of raise he got after 1 year. But when they do the salary calculation for the second year, they start with a bigger number because his salary after 1 year was $52,500, and that's the number they increased by 5%, and 5% of a bigger number is going to be a bigger number. So his raise now is $2,625. So what is constant in exponential growth is the percentage, not the actual dollar amount raise. His raise after 1 year was $2,500. His raise for the second year was more than that. It was $2,625. Hopefully this tutorial helped you understand the difference between what we call linear change and exponential change. And as always, I wish you the best of luck.